The Boötes Void is one of the strangest and most unsettling features of the cosmos, a region so empty it seems as though the universe itself is missing a piece. Astronomers often describe it as looking like a cosmic hole punched into space, a vast sphere of darkness where there should be countless galaxies shining. In a universe that dazzles us with its abundance of stars, nebulae, and superclusters, the Boötes Void feels like a contradiction. Its immensity and emptiness make it unlike almost anything else we've observed, leaving scientists to wonder, how could such a colossal patch of near-nothingness exist in a universe otherwise so full of light and matter? This question alone has transformed the Boötes Void from a simple observation into a cosmic enigma, an unsettling reminder that the universe still keeps some of its deepest secrets hidden within silence and shadow. To truly appreciate the strangeness of the Boötes Void, we first need to understand what astronomers mean when they talk about a cosmic void. The word itself suggests emptiness, but in cosmology, it has a very precise meaning. Voids are enormous regions of space where the density of galaxies is much lower than average. Think of the universe as a grand tapestry, threads of galaxies and clusters forming dense filaments that crisscross one another, weaving the structure of the cosmos itself. Yet between those glowing threads are vast gaps, silent spaces where almost nothing exists. These are the voids, the cold interludes in the cosmic symphony, and they are among the most dominant large-scale structures of the universe. While our eyes are drawn to the brightness of stars and the brilliance of galaxies, it is actually the voids that take up most of the universe's volume, stretching across billions of light-years combined. The irony is profound. Emptiness, not fullness, is the true backdrop of reality. On smaller scales, the universe feels full. Planets orbit stars, stars gather into galaxies, and galaxies clump together into clusters. But as we zoom out, the cosmic pattern becomes clearer. What emerges is the cosmic web, a three-dimensional map of matter distribution that reveals a network of filaments and nodes connected by gravity. The voids exist between these filaments, like bubbles nestled in a froth of galaxies. Their boundaries are defined by where galaxies gather most densely, while their interiors are marked by the absence of light. Yet, these voids aren't simply nothing. They are regions of extreme scarcity. Where you might expect to see thousands of galaxies within a region of a given size, a void may contain only a handful, or sometimes none at all. This gives them an eerie, hollow quality, as though you're staring into the silent lungs of the cosmos. Scientists define cosmic voids by measuring galaxy density in different regions. The universe has an average density, essentially a cosmic baseline for how galaxies are distributed. A void is any area where the density falls below this baseline by a significant margin, often by as much as 80 to 90%. These voids vary in size, with some only spanning a few million light-years across, while others, like the Boötes Void, balloon to sizes so immense they almost defy comprehension. Yet no matter their size, they serve as the empty counterparts to the bright and bustling galactic clusters that dominate cosmic surveys. Voids are not rare curiosities. They are an essential part of how the universe organizes itself on the largest scales. In fact, current cosmological models predict that voids make up about 80% of the observable universe's volume, though they contain only about 10% of its galaxies. The Boötes Void stands out because it takes this emptiness to such an extreme that it feels like an anomaly, even among voids. One of the most intriguing aspects of voids is how they tell us about the early universe. After the Big Bang, the cosmos was not perfectly uniform. Tiny fluctuations in density rippled across the infant universe, creating slightly denser regions where gravity would eventually pull matter together to form stars and galaxies. But equally important were the underdense regions, areas where matter was sparse from the very beginning. Over billions of years, these regions grew emptier as matter was drawn away toward the denser filaments. In this way, cosmic voids are not accidents of cosmic geography, but natural outcomes of the universe's initial conditions. They represent the shadow of creation itself, the places where galaxies failed to gather, leaving behind immense cavities of stillness. What makes voids so compelling is that, despite their emptiness, they are not irrelevant to cosmic evolution. Quite the opposite. They are vital for testing our theories of physics and cosmology. Their sheer scale amplifies the subtle effects of dark matter and dark energy, making them natural laboratories for probing forces that are otherwise elusive. Because voids are so underdense, galaxies inside them feel weaker gravitational pulls than galaxies in crowded clusters. This isolation changes how they evolve, how their stars are born, and how they interact with surrounding matter. For astronomers, this means studying galaxies inside voids offers a chance to see how cosmic conditions shape the very fabric of galactic life. Voids also serve as testing grounds for some of the biggest mysteries in science, particularly dark energy, the enigmatic force driving the accelerated expansion of the universe. By observing how voids stretch and grow over time, researchers can refine their measurements of dark energy's influence on cosmic scales. Voids also sharpen our understanding of dark matter. Even though they appear empty, voids are thought to still contain dark matter, the invisible substance that makes up most of the universe's mass. Mapping the distribution of voids helps cosmologists constrain theories about how dark matter interacts and how it sculpts the overall cosmic web. In this sense, voids are not empty at all. They are silent canvases where the faint fingerprints of the universe's deepest laws can be read. The story of the Boötes Void truly begins in the mid-1980s, when astronomers were in the midst of an ambitious effort to chart the large-scale structure of the universe. At that time, mapping galaxies was far from easy. Observations required painstaking telescope surveys, where astronomers recorded the positions of galaxies one by one, gradually building up a three-dimensional map of the cosmos. It was during one such survey, led by Robert Kirshner and his colleagues in 1981, and later published in 1987, that this incredible discovery came to light. As they analyzed the distribution of galaxies in the direction of the constellation Boötes, they noticed something utterly bizarre: an enormous stretch of sky that was almost completely devoid of galaxies. Instead of the expected smattering of galactic dots, they were confronted with an emptiness, a cosmic hole so vast that it seemed almost like a mistake in the data. Yet, as they checked and rechecked, the reality of the gap became undeniable. This discovery shocked the scientific community because it was not simply another small void or irregularity. Voids had already been identified as part of the large-scale cosmic structure, but nothing even remotely close to the size of the Boötes Void had ever been observed. The region they stumbled upon spanned an astonishing 330 million light-years across, making it one of the largest known voids in the universe. To put this into perspective, it is more than twice the size of the Great Attractor region, and many times larger than the Virgo supercluster, which contains our own local group of galaxies, including the Milky Way. The idea that such an immense stretch of space could exist with almost no galaxies in it was nothing short of revolutionary. For astronomers, the Boötes Void wasn't just an observational oddity. It was a direct challenge to the models of cosmic structure formation that existed at the time. According to the best theories, the universe's large-scale structure should have been shaped by the gravitational pull of dark matter and the expansion from the Big Bang. While voids were a natural outcome of these processes, the sheer scale of Boötes seemed excessive. It was almost too big, too empty, and too abrupt to fit neatly into existing models. The scientific world was left grappling with the possibility that there might be mechanisms at work in shaping the universe that had not yet been fully understood. The initial surveys of the Boötes Void revealed that while it was not entirely devoid of galaxies, the count was shockingly low. Instead of the thousands of galaxies astronomers would have expected to find within such a colossal volume of space, there were only about 60. That number, though not zero, was so disproportionately small that it only deepened the mystery. The galaxies that did exist inside the void appeared to be widely scattered, like lonely islands in an ocean of darkness. Their isolation raised immediate questions about how such galaxies could form and survive in such extreme solitude. Did they evolve differently from galaxies in denser regions? Were they relics of some ancient cosmic process that left them stranded in a sea of emptiness? These questions sparked decades of research that continues to this day. The discovery of the Boötes Void also revealed the importance of galaxy surveys in uncovering the hidden architecture of the universe. Before such surveys, the cosmos was often imagined as being somewhat uniform, galaxies scattered more or less evenly across space, but the revelation of structures like the Boötes Void forced astronomers to rethink this assumption. Instead of uniformity, the universe displayed striking patterns, dense filaments, massive clusters, and, equally important, yawning voids. This was one of the first concrete signs that the universe was not random in its large-scale layout, but was instead governed by deep physical laws that sculpted the distribution of matter into a vast cosmic web. The sheer surprise of the Boötes Void's discovery also spilled over into the public imagination. It was given the nickname the Great Nothing, a phrase that captures its eerie significance. Journalists and science communicators began to describe it not merely as a scientific curiosity, but as one of the most unsettling features of the cosmos. While galaxies, stars, and nebulae inspire awe with their beauty, the Boötes Void inspires awe of a different kind. The awe of absence, of silence, of scale so vast and so barren that it challenges the human mind to even conceptualize it. When we speak of the Boötes Void, its defining feature is its size, an immensity so staggering that it stretches the limits of human comprehension. This vast cosmic cavity measures about 330 million light-years across, making it one of the largest voids ever discovered in the observable universe. To truly grasp what this number means, we have to break it down into scales we can at least attempt to relate to. A single light-year is the distance that light, the fastest thing in existence, can travel in 1 year, roughly 9.46 trillion kilometers. Now multiply that distance by 330 million. The result is a number so large it ceases to feel real, an abyss spanning across distances greater than the imagination can comfortably hold. If you were somehow able to cross this void at the speed of light, it would take you more than 330 million years to go from one end to the other. To put that into perspective, 330 million years ago on Earth, the first forests were just beginning to spread across the planet, and the age of the dinosaurs was still far in the future. The time it would take to traverse the Boötes Void is longer than the existence of most forms of life that ever evolved on our planet. Now consider that our entire Milky Way galaxy, home to hundreds of billions of stars and planets, is about 100,000 light-years across. The Boötes Void dwarfs this scale entirely. You could line up over 3,000 Milky Way galaxies side by side, and they would barely stretch across its expanse. Even more striking is when we compare it to the local group, the cluster of galaxies that includes the Milky Way, the Andromeda Galaxy, and about 50 smaller companions. The local group spans just a few million light-years across. The Boötes Void, at 330 million light-years, could swallow the local group more than 100 times over and still have vast stretches of emptiness left untouched. It is not simply large, it is incomprehensibly so, dwarfing the galactic neighborhoods we are familiar with into insignificance. Even the Virgo supercluster, the massive collection of thousands of galaxies to which our local group belongs, pales in comparison. The Virgo supercluster stretches about 110 million light-years across, immense by any human standard, yet still only about a third of the size of the Boötes Void. In this way, the void is not just another gap in the universe, but one of the most colossal features of cosmic architecture ever found. It is a cavern of darkness, a cosmic desert larger than entire superclusters of galaxies, standing as a stark reminder that emptiness, not abundance, dominates the universe on its grandest scales. The sheer volume of the Boötes Void adds to the sense of astonishment. Its spherical shape encompasses a region so vast that, if you calculated its total volume, you'd find it holds over 236,000 times the volume of the Milky Way galaxy. And yet, within this titanic space, astronomers have only been able to confirm about 60 galaxies. This means that galaxies are so spread out inside the void that the average distance between them is staggering, compared to what we find in denser cosmic neighborhoods. For context, the Milky Way is only about 2.5 million light-years away from Andromeda, its nearest large galactic neighbor. Inside the Boötes Void, the separation between galaxies can stretch tens or even hundreds of millions of light-years. Each galaxy inside is like a solitary lighthouse standing in an endless ocean of darkness, so far from its companions that their light may never meaningfully overlap. The immensity of the Boötes Void also forces us to think about cosmic time in new ways. The light we see from the farthest edge of the void today has taken 330 million years to reach us. In that time, entire species on Earth have come and gone, continents have shifted, and countless stars have been born and died. This means that even our perception of the void is bound up in history. We are looking not at what it is now, but at what it was hundreds of millions of years ago. The very act of observing something so large stretches our concepts of time and space to their limits. What makes this void's dimensions even more mysterious is the contrast it provides against the rest of the observable universe. The observable universe is about 93 billion light-years across, filled with more than 2 trillion galaxies. Within that immensity, one might think that no single feature could stand out. Yet the Boötes Void does exactly that. Its 330 million light-year expanse may only be a small fraction of the observable universe, but its existence as a gaping sphere of near-nothingness sets it apart. Most voids we know of are significantly smaller, ranging from 20 to 100 million light-years across. To encounter one 3 times or even more than 10 times larger than the average is akin to discovering a canyon on Earth that stretches not for miles, but for thousands of miles. It feels disproportionate, extreme, as though the universe overreached in carving out this particular hollow. Another way to grasp its size is through comparison with human exploration. Our most advanced spacecraft, such as Voyager 1, launched in 1977, has been traveling for nearly 50 years and has only just left the outer boundary of our solar system. At its current speed of about 17 kilometers per second, it would take Voyager more than 6 trillion years to cross the Boötes Void, a number nearly 500 times the current age of the universe itself. Such figures highlight not only the immensity of the void, but also the smallness of humanity's reach into space. The Boötes Void reminds us that no matter how far we've come technologically, we remain anchored to a tiny island of matter within an overwhelmingly empty sea. The universe, as we have come to know it, is a place of overwhelming abundance. Everywhere astronomers point their telescopes, they uncover galaxies scattered across the heavens, like diamonds in an endless black sea. Our observable universe, stretching across 93 billion light-years, is estimated to contain more than 2 trillion galaxies, each one hosting billions, sometimes even trillions, of stars. The Hubble Deep Field and its successor, the Hubble Ultra Deep Field, revealed that even when you stare into a seemingly empty patch of sky, no larger than a grain of sand held at arm's length, the darkness is filled with thousands of galaxies. This discovery has reshaped our understanding of the cosmos, showing that galaxies are not rare jewels, they are the very fabric of the universe itself. And yet, against this backdrop of cosmic richness lies the great contradiction. The Boötes Void, a vast region of space that seems to defy the universe's natural tendency to overflow with galaxies. When you consider how crowded the observable universe usually appears, the Boötes Void becomes even more extraordinary. In most regions of space, especially those mapped by large-scale galaxy surveys, galaxies cluster into filaments, webs, and dense superclusters. Even voids, which are defined by their emptiness, usually contain a fair scattering of galaxies. They are not total vacuums, but rather underpopulated neighborhoods where galaxies are fewer and farther between. The Boötes Void, however, is an extreme outlier. Within its 330 million light-year span, a volume that could contain thousands upon thousands of galaxies if it were like any typical region of space, astronomers have found only about 60. This is like looking out across a great city skyline where you would expect to see a forest of glowing towers, but instead you find only a handful of scattered lampposts flickering in the distance. This contrast makes the Boötes Void feel almost unnatural. The universe, which we so often describe as filled with stars, galaxies, and cosmic light, suddenly seems hollow in this region. It is as though the cosmos itself is broken here, its vibrant structure interrupted by silence. While we know scientifically that this emptiness is a result of natural processes tied to the way matter was distributed in the early universe, the emotional weight of it still lingers. For many, the Boötes Void represents not just an astronomical oddity, but an existential puzzle. How can the same universe that overflows with galaxies also harbor a region that is nearly barren, like a wound carved into the cosmic web? What amplifies this sense of strangeness is the scale at which the contrast occurs. If the Boötes Void were small, its emptiness might be overlooked as a statistical anomaly. But its immensity, combined with its lack of galaxies, makes it one of the most profound irregularities in cosmic structure. Astronomers often describe the large-scale universe as a kind of foam, with filaments forming the walls of bubbles and voids occupying the interior. In this analogy, the Boötes Void isn't just another bubble. It is a superbubble, a cavern so vast that it dwarfs almost everything else around it. And yet, unlike many voids that at least hold faint galaxies or smaller structures, the Boötes Void seems stripped almost bare, as though even the universe's tendency to create galaxies faltered in this one particular region. The fact that the observable universe is so richly populated only makes this emptiness stand out more starkly. Our own Milky Way is part of a bustling neighborhood within the local group, which is itself nestled in the Virgo supercluster, which in turn is just one filament of the even larger Laniakea supercluster. In all directions, galaxies stretch outward, forming chains, walls, and clusters. It is within this grand architecture of abundance that the Boötes Void appears as an interruption, an almost dissonant note in the cosmic symphony. In the same way a single silence in a piece of music can feel louder than any sound, the Boötes Void feels louder in its emptiness than the countless galaxies that surround it. For cosmologists, this makes the Boötes Void more than just a curiosity. It forces them to ask, why here? Why does the universe, which otherwise teems with galaxies, allow for such extreme emptiness? Is it purely the result of chance fluctuations in the early density field of the universe? Or is there something deeper at work, something about the laws of physics that predisposes certain regions to become deserts while others flourish with galaxies? These questions elevate the Boötes Void from being a strange gap in space to being a scientific riddle that could refine our understanding of cosmic evolution. When astronomers first confronted the Boötes Void, one of the immediate questions they asked was simple: how many galaxies are actually inside this enormous cavern of space? After all, even voids, by definition among the emptiest regions in the cosmos, are not true vacuums. They still contain dark matter, gas, and usually a fair sprinkling of galaxies. Yet, the Boötes Void turned out to be an extreme case, an emptiness so profound that it stood out as an anomaly even among voids. In a space 330 million light-years across, one would normally expect to find thousands upon thousands of galaxies, perhaps tens of thousands, depending on the density of the region. Instead, astronomers have been able to confirm only around 60 scattered galaxies within its boundaries. 60 galaxies may sound like a lot at first glance, but in cosmic terms it is astonishingly few, like finding only a handful of houses scattered across a region the size of a continent. To appreciate just how unusual this is, consider the average expectations of galaxy distribution. The observable universe has a fairly uniform mean density when scaled to very large distances, meaning that while galaxies are clumped into filaments and clusters, the overall numbers balance out. Within a volume equivalent to the Boötes Void, cosmologists would typically predict thousands of galaxies, ranging from massive spirals like the Milky Way to elliptical giants and countless dwarfs. The fact that the Boötes Void contains fewer than 1% of that expected number highlights its extraordinary emptiness. This is why it captured so much attention when it was first mapped. It wasn't just large, it was barren in a way that defied easy explanation. The galaxies that do exist within the Boötes Void are fascinating precisely because of their rarity. They are loners, isolated from the galactic filaments that define the cosmic web. Most galaxies in the universe have neighbors. They are gravitationally bound in groups or clusters, interacting, colliding, and merging over cosmic timescales. These interactions fuel star formation, trigger supernovae, and shape the evolutionary paths of galaxies. Inside the Boötes Void, however, galaxies are so far apart that such interactions are vanishingly rare. They live in solitude, evolving in near isolation. For astronomers, these galaxies are windows into how environment shapes galactic development. Do they form stars at the same rates as galaxies in denser regions? Do they have different morphologies because they grow without collisions? Studying them offers a natural laboratory for testing these questions. One particularly interesting aspect of galaxies and voids is their tendency to be smaller and dimmer than galaxies in crowded environments. These so-called dwarf galaxies often go unnoticed in large surveys because of their faintness. It is possible, perhaps even likely, that the Boötes Void contains more galaxies than the 60 that have been catalogued so far, but that many of them are too faint for our current instruments to detect. Future surveys using advanced telescopes, such as the James Webb Space Telescope, or next-generation ground-based observatories, may uncover additional hidden galaxies lurking within the darkness. Even so, no matter how many faint dwarfs might be discovered, the numbers will remain far below what would be expected for a volume of space that vast. This means that the Boötes Void's emptiness is real and fundamental, not simply a matter of missed detections. The extreme scarcity of galaxies inside the void also raises fascinating cosmological questions. If galaxies are so rare within it, what does that imply about the distribution of dark matter? Dark matter, which makes up most of the universe's mass, plays a crucial role in galaxy formation by providing the gravitational scaffolding around which galaxies assemble. If there are so few galaxies in the Boötes Void, does that mean dark matter is also unusually underdense there? Or is dark matter present in large quantities but somehow failing to seed galaxies? These questions make the Boötes Void a key site for probing the mysteries of dark matter and the processes that drive cosmic structure formation. The 60 galaxies that have been identified in the Boötes Void are scattered like faint beacons across an otherwise empty landscape. To put their distribution into perspective, consider that within our local group alone, a relatively small cosmic neighborhood, there are over 50 galaxies, including the Milky Way, Andromeda, and dozens of dwarf galaxies. The Boötes Void is more than 100 times larger in scale than the local group, and yet it holds only a similar number of galaxies. This stark disparity is what makes the void feel so alien. It is not just empty compared to the densest parts of the universe. It is empty compared to even the average regions of space. Astronomers have also studied the placement of the galaxies within the Boötes Void, and one pattern that emerges is that many of them tend to lie near the edges rather than the center. This reflects the broader structure of the cosmic web. Matter flows toward filaments and walls, leaving the interiors of voids particularly barren. The galaxies that are deep inside the void are true cosmic outliers, stranded in near total solitude. Their isolation raises tantalizing questions about their histories. Did they form there, born in a sparse region of the early universe? Or were they once closer to filaments and somehow migrated inward? These possibilities connect directly to broader theories of galaxy migration and cosmic evolution. When trying to comprehend the staggering immensity of the Boötes Void, the human mind naturally seeks points of comparison, anchors that ground such incomprehensible distances to scales we can at least imagine. And so, to truly appreciate its emptiness, we must compare it to the cosmic structures we know best, our own local group of galaxies, and the much larger Virgo supercluster, both of which give us a sense of the cosmic architecture surrounding us. These familiar structures, vast in their own right, suddenly seem minuscule when measured against the yawning emptiness of the Boötes Void. Let's start small, or rather with the largest structure we can comfortably call home. The local group is our immediate galactic neighborhood, containing the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and more than 50 dwarf galaxies bound together by gravity. The local group spans about 10 million light-years across, a distance so immense it takes light itself, moving at 300,000 kilometers per second, millions of years to cross. To us, this is enormous. It defines our cosmic community, the boundary of the galactic environment within which the Milky Way resides. Yet the Boötes Void dwarfs the local group so completely that the comparison borders on absurd. At 330 million light-years across, the void is more than 30 times larger in diameter. But because volume scales with the cube of size, the disparity is even greater in 3 dimensions. The Boötes Void has a volume about 27,000 times larger than that of the local group. Imagine a small village compared to a vast desert stretching across a continent, and you begin to sense just how outmatched our local galactic neighborhood is against this chasm of emptiness. Expanding outward, let us consider the Virgo supercluster, of which the local group is but one tiny part. The Virgo supercluster is enormous, stretching roughly 110 million light-years across and containing thousands of galaxies bound into clusters and filaments. It is a structure so large that it took decades of astronomical surveys to fully map its extent. Within the Virgo supercluster, galaxies arrange themselves in long chains and sheets, clustering into massive gravitational wells. For many years, it was considered one of the grandest structures in the universe known to humanity. Yet, when set beside the Boötes Void, even the Virgo supercluster feels humbled. The void is 3 times wider and nearly 30 times more voluminous. In effect, you could fit the entire Virgo supercluster inside the Boötes Void multiple times over, and still, vast stretches of darkness would remain untouched. The thought of placing an entire bustling metropolis of galaxies into a space that still looks overwhelmingly empty is a powerful testament to just how strange and exceptional this void truly is. The disparity becomes even more striking when you consider density. The Virgo supercluster, for all its expanse, is a place teeming with galaxies, thousands upon thousands of them bound together in a rich tapestry. The local group, though smaller, also contains dozens of galaxies within its 10 million light-year span. In contrast, the Boötes Void offers only about 60 galaxies across a space hundreds of millions of light-years in diameter. This means that where the Virgo supercluster provides a bustling metropolis of cosmic activity, the Boötes Void provides the equivalent of a barren wasteland with only a few scattered outposts. Imagine comparing the traffic of a thriving megacity to the silence of a desert plain with just a handful of villages. This is the scale of contrast that astronomers grapple with when they confront the Boötes Void. But to make the scale even clearer, consider the speed of light once more. Crossing the local group at light speed would take about 10 million years, a span longer than the entire history of human evolution, but still imaginable on cosmic terms. Crossing the Virgo supercluster at light speed would take 110 million years, a time span older than most of the dinosaurs that ever walked Earth. Crossing the Boötes Void, however, would take 330 million years, a time span so long it predates the very rise of flowering plants on Earth. In other words, if you began a journey across the Boötes Void at the speed of light the moment the first primitive reptiles began walking the land, you still wouldn't have reached the other side by today. This kind of temporal enormity makes the void not just large, but profoundly disorienting, stretching our sense of history as well as our sense of space. The scale comparison also highlights a deeper truth about the structure of the universe. In the grand balance of cosmic architecture, clusters and voids define one another. The Virgo supercluster exists as a great concentration of matter precisely because other regions, like the Boötes Void, are relatively empty. Matter is not evenly spread, but instead distributed unevenly, pooling into dense filaments and draining from underdense voids. The enormity of the Boötes Void emphasizes this contrast in its most extreme form, showcasing just how imbalanced, and yet how beautifully patterned, the universe truly is. To understand why the Boötes Void exists, and why such an enormous emptiness could be carved into the very fabric of the universe, we need to zoom out and consider the largest patterns known to science, the cosmic web. On small scales, the universe appears random, stars within galaxies, galaxies scattered across the sky. But as astronomers mapped the cosmos on ever larger scales, something extraordinary emerged. Galaxies are not scattered haphazardly at all. Instead, they are arranged in an intricate network of filaments, walls, and nodes, forming a structure so vast and interconnected that it resembles a web stretching across the universe. This web is the true skeleton of the cosmos, and the Boötes Void is one of its most dramatic expressions, a bubble left behind in the gaps between threads of light. The cosmic web is the direct result of the universe's earliest moments. In the aftermath of the Big Bang, the universe was not perfectly smooth. Tiny fluctuations in density, minute ripples in the otherwise uniform plasma, seeded the gravitational scaffolding of everything we see today. In regions slightly denser than average, gravity pulled matter inward, amplifying the clumps. Over billions of years, these clumps grew into filaments and clusters of galaxies. Meanwhile, the underdense regions became increasingly empty as matter drained away into the denser structures. What emerged is the web we observe today. Bright filaments where galaxies and clusters reside, and dark voids where matter is scarce. The Boötes Void is an extreme example of one of these voids, a vast bubble created by the gravitational flow of matter away from its center and into the surrounding walls. When astronomers use large-scale surveys to map galaxies, the cosmic web becomes visible in breathtaking clarity. Imagine looking at a three-dimensional sponge, with strands crisscrossing and bubbles filling the gaps between them. That is the universe on scales of hundreds of millions of light years. Galaxies cluster tightly along the filaments, forming walls that stretch for billions of light years, while the voids make up the spaces in between. Most voids are tens of millions of light years across, sometimes 100 million. But the Boötes Void, at 330 million light years, is a giant among them, a cavernous gap that makes the cosmic web's bubble-like nature strikingly apparent. It is as if the universe exhaled, and in doing so, left behind a hollow so immense it dwarfs entire superclusters of galaxies. The galaxies that lie within and around the Boötes Void provide clues to this cosmic web connection. Most are not scattered randomly. Instead, they cluster along the edges of the void, forming a kind of spherical boundary that marks where the filaments intersect. The void itself is not an isolated phenomenon. It is part of the greater architecture of the web. In this sense, the Boötes Void is not a mistake or an exception, but a natural feature of the universe's large-scale design. It is simply an unusually large bubble in the foam-like structure of the cosmos. Still, its enormity makes it one of the most extreme and captivating examples we have found. The cosmic web also reveals a deeper truth. The universe is mostly empty space. Filaments, clusters, and galaxies may dominate our imaginations because they glow with light, but they represent only a tiny fraction of the universe's volume. Voids, like the Boötes Void, occupy the majority. This challenges our perception because our experience is grounded in fullness: planets, stars, light. But the web shows us that emptiness is the rule, and matter is the exception. In this sense, the Boötes Void is not just a curiosity, it is a window into the universe's most fundamental truth. Computer simulations of cosmic evolution, such as the Millennium simulation, have beautifully confirmed this web-like pattern. When cosmologists input the physics of the Big Bang, dark matter, and gravity into their models, what emerges after billions of simulated years is a universe of filaments and voids, nearly identical to what we observe. And within these simulations, enormous voids like Boötes appear as natural outcomes of cosmic evolution, though their extreme size still raises eyebrows. This alignment between theory and observation reinforces the idea that the Boötes Void is an organic piece of the universe's architecture, even if it is among the largest known. What makes the Boötes Void particularly fascinating is how it connects both visually and conceptually to the surrounding filaments. If you could drift through it and look back toward its edges, you would see galaxies forming a faint shell, like a bubble wall, glowing weakly against the blackness. It would be like standing in the center of a cosmic cathedral, the vast dome above you defined not by solid stone, but by the faint glimmer of galaxies outlining the void's boundary. That image captures the essence of the cosmic web, a structure defined not by what is present, but by the geometry of absence. The question of why voids like the Boötes Void exist, why they are so profoundly empty compared to the rest of the universe, takes us back to the very beginning of cosmic history, to the first fractions of a second after the Big Bang. At first glance, it seems counterintuitive. If the universe was born from a single event, shouldn't matter be spread evenly everywhere? Shouldn't galaxies fill space uniformly like stars on a clear night sky? But the truth is far more subtle and fascinating. Voids are not accidents. They are the natural consequence of the way the universe unfolded from its earliest moments. Their existence tells us about density fluctuations, the growth of cosmic structure, and the way gravity sculpts matter across billions of years. In the first instant after the Big Bang, the universe was a hot, dense plasma of particles and radiation. To our eyes, it might have appeared perfectly smooth, but in reality it contained tiny fluctuations, slight variations in density as small as 1 part in 100,000. These were quantum ripples stretched across the cosmos during a period known as inflation, when the universe expanded exponentially in a fraction of a second. Inflation magnified microscopic variations into macroscopic imprints, seeding the universe with a kind of cosmic fingerprint. These tiny fluctuations became the scaffolding upon which the entire large-scale structure of the universe would form. Some regions were slightly denser than average, while others were slightly less dense. Over billions of years, gravity pulled matter toward the denser regions, amplifying the contrast. The overdense regions grew into filaments, clusters, and galaxies. The underdense regions, on the other hand, were drained of matter, becoming voids. This process explains why voids exist in the first place. They are the natural counterparts of galaxies and clusters. Without voids, there could be no filaments. Without scarcity, there could be no abundance. They are two sides of the same coin, written into the universe from its earliest fluctuations. The Boötes Void, then, is not a mistake. It is a magnified expression of these initial conditions, an underdensity that grew emptier over cosmic time as surrounding matter flowed into denser regions. Its extreme size, however, raises questions about just how large such underdensities can grow, and whether its enormity represents a rare statistical outlier or hints at physics we do not fully understand. Another key to understanding why voids are so empty lies in the way matter flows through the cosmic web. Imagine the universe as a landscape of hills and valleys, with density fluctuations as the terrain. Matter naturally rolls downhill, pulled toward the valleys of higher density. Over billions of years, galaxies form and cluster in those valleys, the filaments and nodes of the cosmic web. The hills, representing underdense regions, become increasingly barren as matter is pulled away. The Boötes Void is essentially one of the largest hills in this cosmic landscape, an enormous region that has been drained of matter as gravity funneled it elsewhere. This flow continues even today, as matter slowly migrates toward denser filaments, leaving the voids more and more empty. The size of the Boötes Void also raises questions about cosmic variance, the idea that the universe, while uniform on the largest scales, still contains statistical outliers. In most regions, voids are tens to hundreds of millions of light-years across, but the Boötes Void, at 330 million light-years, is near the extreme end of possibility. It may simply be one of the universe's rarest anomalies, a void born from an unusually large underdensity seeded in the early universe. Cosmologists sometimes describe this as a fluke of the dice rolled by inflation. If so, the Boötes Void is an extraordinary stroke of cosmic luck, or unluck, that we happen to observe from our vantage point. However, some scientists argue that its size may hint at more than statistical chance. Could there be deeper physical processes at work that make some regions of the universe emptier than others? One possibility is that dark energy, the mysterious force accelerating the universe's expansion, exacerbates the emptiness of voids. In underdense regions where gravity is weaker, the repulsive effect of dark energy may dominate, stretching space faster than in denser areas. This would make voids expand more quickly than filaments, enhancing their emptiness over time. If true, voids are not just byproducts of density fluctuations, but active arenas where dark energy leaves its fingerprints. Studying them could therefore help us decode the nature of this mysterious cosmic force. There is also the role of dark matter to consider. Galaxies form when gas collapses into the gravitational wells created by dark matter halos. In regions where dark matter density is low, halos are scarce, and so galaxies cannot form in abundance. The Boötes Void may simply be a place where dark matter is unusually thin, leaving very few gravitational seeds for galaxies. If that is the case, then the void's emptiness is not just a lack of visible matter, but also a lack of the invisible framework required for galaxies to exist in the first place. This connection between voids and dark matter is why astronomers study their shapes and sizes so closely. By mapping voids, we indirectly map the unseen dark matter scaffolding that underpins the universe. Another explanation involves the idea of cosmic migration. Over billions of years, galaxies and smaller structures may drift away from voids and toward denser filaments. This process, known as void evacuation, gradually strips voids of their contents, leaving behind only a sparse population of galaxies. If the Boötes Void has been slowly losing galaxies for billions of years, then its current state may reflect an advanced stage of this process, an old void that has been thoroughly emptied by the gravitational tides of the cosmic web. Of course, theories must contend with one puzzling fact. Why does the Boötes Void stand out so much compared to other voids? Why aren't there more voids of comparable size? Some researchers argue that we may not have mapped the universe deeply enough to know. After all, the observable universe is vast, and our surveys are still incomplete. It is possible that other Boötes-like voids exist, waiting to be uncovered by future sky mapping projects. If we find more of them, then perhaps the Boötes Void is not as anomalous as it seems. It may simply be part of a larger pattern. If we do not, then its singularity demands a deeper explanation. When considering why voids like the Boötes Void remain so profoundly empty, one cannot avoid the influence of one of the universe's most mysterious forces, dark energy. This invisible component of the cosmos, first discovered in the late 1990s through observations of distant supernovae, is thought to make up nearly 70% of the universe's total energy content. Its defining characteristic is that it drives the accelerated expansion of the universe, pushing galaxies away from one another at an ever-increasing rate. While its effects are felt everywhere, they are especially noticeable in cosmic voids, where the lack of matter allows dark energy to dominate with little resistance. For the Boötes Void, this means its emptiness is not simply a frozen relic of the past, but an evolving feature continually shaped by dark energy's expansive push. To understand why dark energy plays such a crucial role, it helps to think about the balance of forces in different regions of the universe. In dense areas, such as clusters and superclusters, gravity is strong. The combined pull of thousands of galaxies and their associated dark matter halos counteracts the accelerating expansion, slowing down the rate at which these structures stretch apart. Matter clumps and holds together despite the universe's expansion, forming the cosmic filaments and walls we observe. In contrast, in underdense regions like voids, gravity's pull is weak. There are so few galaxies and so little dark matter that nothing significantly resists the expansion. As a result, voids not only expand along with the universe, they expand faster than denser regions. This differential stretching exaggerates their emptiness, creating what some cosmologists describe as super-expanding regions of space. The Boötes Void, then, may be an especially dramatic example of this phenomenon. Already seeded as an underdensity by the fluctuations of the early universe, it has been stretched and deepened over billions of years by the relentless push of dark energy. Galaxies and matter that once lingered closer to its center have been pulled outward, migrating toward the denser walls of the surrounding filaments. This creates a self-reinforcing cycle. The emptier the void becomes, the less gravity can resist dark energy, and the faster it expands. Over cosmic timescales, this runaway effect ensures that voids like Boötes grow larger and more desolate, while the surrounding filaments grow richer and more concentrated. What is fascinating is that voids provide a natural laboratory for studying dark energy. Because they are dominated by expansion rather than gravitational clumping, they amplify the effects of dark energy in ways that dense regions do not. Astronomers can measure the shapes, sizes, and growth rates of voids to infer how dark energy operates. For example, if dark energy is a simple cosmological constant, as Albert Einstein once proposed, then voids should expand in a predictable way that matches the standard model of cosmology. But if dark energy evolves over time, or if it interacts with matter in ways we don't yet understand, voids might expand differently. By observing extreme voids like Boötes, cosmologists hope to tease out these subtle differences, using emptiness itself as a measuring stick for the universe's fate. Another striking consequence of dark energy's dominance in voids is how it alters the flow of matter. In denser parts of the universe, galaxies often fall together, colliding and merging under the pull of gravity. In voids, the opposite happens. Galaxies drift apart, pulled toward the edges and away from the interior. Over time, this evacuation leaves the centers of voids increasingly barren. The Boötes Void is a vivid example of this process, with most of its galaxies residing near its boundaries, while the central regions remain almost completely devoid of light. Without dark energy's persistent push, this process would be slower, and voids might not be nearly as empty as they appear today. Dark energy also raises fascinating questions about the future of voids like Boötes. If the current acceleration continues unchecked, voids will become even larger and emptier over the next billions of years. Galaxies along their edges will be pulled farther apart, and the already isolated galaxies within them will drift into deeper solitude. Eventually, if acceleration continues indefinitely, voids could dominate the cosmic landscape to an even greater degree than they already do, leaving behind a universe that is, on the grandest scales, more void than filament. In that far future, the Boötes Void might be seen not as an anomaly, but as a preview of the universe's ultimate destiny, a cosmos of expanding emptiness where islands of matter become ever more isolated. The study of voids under the influence of dark energy also offers a unique perspective on one of the greatest mysteries in physics. We do not yet know what dark energy truly is. It could be a cosmological constant, a property of space itself. It could be a dynamic field that evolves over time. Or it might even hint at a flaw in our understanding of gravity on cosmic scales. Each of these possibilities would affect voids differently. By carefully mapping voids like Boötes, scientists hope to turn these vast empty spaces into tools for probing the unknown. Paradoxically, the absence of galaxies may tell us more about the fundamental nature of the universe than the presence of galaxies ever could. When we describe the Boötes Void as empty, it is easy to imagine a colossal nothingness, a sphere of absolute vacuum stretching across 330 million light-years. But in truth, even the most barren cosmic void is not completely devoid of content. What lies inside the darkness of the Boötes Void is more subtle, more hidden, and perhaps more fascinating than one might expect. Though galaxies are exceedingly rare, the void is not truly empty. Instead, it harbors invisible matter, stray gas, and possibly countless faint dwarf galaxies that elude even our most advanced instruments. The darkness of the void, therefore, is not absence. It is the concealment of forms of matter and energy that challenge our ability to detect them. The most significant component lurking inside the Boötes Void is dark matter. This mysterious substance, making up about 27% of the universe's total content, does not emit or absorb light. We cannot see it directly, but we know it is there because of its gravitational influence. Galaxies rotate faster than they should if they contained only visible matter, and large-scale cosmic structures could not have formed without dark matter providing the gravitational scaffolding. Even inside voids, where visible galaxies are sparse, dark matter is still present. Its density may be lower than in filaments or clusters, but it still pervades the space, shaping the faint gravitational landscape. In fact, the Boötes Void may be one of the best natural laboratories for studying how dark matter behaves in underdense environments. Without the noise of dense galaxy clusters, its subtle gravitational pull can be traced more clearly, offering clues about the invisible framework of the universe. Alongside dark matter, cosmic voids like Boötes also contain gas, both hydrogen and helium, the primordial elements forged in the first minutes after the Big Bang. This intergalactic medium, though incredibly diffuse, stretches throughout the universe. In filaments, it condenses into denser clumps where stars and galaxies form. In voids, it remains thin and faint, often undetectable by ordinary telescopes. However, astronomers have begun to trace this hidden gas by observing how it absorbs the light from distant quasars, active galactic nuclei so luminous they shine across billions of light-years. When quasar light passes through the faint gas inside voids, it leaves behind subtle absorption lines, allowing scientists to map the otherwise invisible contents of these dark regions. Such studies reveal that voids, while visually barren, are still threaded with the raw material of the cosmos, though stretched so thin it is nearly imperceptible. Then there are the galaxies themselves, the few that exist inside the Boötes Void, along with the many that may remain hidden. As of now, astronomers have confirmed roughly 60 galaxies within the void, but this number may only scratch the surface. The majority of galaxies in the universe are small and faint dwarf galaxies, many of which are too dim to be detected even with modern surveys. These galaxies contain far fewer stars than giants like the Milky Way, often only a few million compared to the Milky Way's hundreds of billions. Inside the Boötes Void, where galactic evolution is stunted by isolation, such dwarfs may dominate. They are difficult to see, but new instruments like the James Webb Space Telescope are pushing the boundaries of detection, offering the tantalizing possibility of uncovering hidden galaxies scattered across the void's vast expanse. If these dwarfs exist in significant numbers, they would fill in part of the mystery, showing that while the void is underpopulated, it is not quite as barren as it appears. Another layer of intrigue comes from the possibility of hidden structures too faint or diffuse to register in our current surveys. For example, faint stellar streams, remnants of small galaxies torn apart by gravity, may crisscross the void, detectable only with extremely sensitive instruments. Gas filaments too diffuse to condense into galaxies may also thread through its darkness, forming ghostly connections to the surrounding cosmic web. These faint structures would reveal that even inside the largest voids, the universe maintains continuity with the grand cosmic web, though at levels almost invisible to us. The galaxies that do shine within the Boötes Void also tell a unique story. Isolated from the crowded environments of clusters, they evolve differently, often more slowly. Without frequent collisions or mergers, they may preserve characteristics of the early universe that are erased in denser regions. Their star formation rates, morphologies, and chemical compositions may all bear the imprint of life in solitude. To study them is to peer into a cosmic experiment. What happens when a galaxy grows up in isolation, without the gravitational interactions that shape most others? In this sense, every galaxy inside the Boötes Void is a rare treasure, offering insights that cannot be obtained elsewhere. And then, of course, there is the pervasive presence of dark energy. While not a substance that fills the void, in the conventional sense, its effects are amplified there. With so little matter to resist it, the accelerated expansion of the universe operates at full strength inside voids, subtly influencing the movement of galaxies and gas. The Boötes Void, in this way, is not simply a container of hidden matter and faint galaxies. It is also a region where the very laws of cosmic expansion play out most clearly, stretching space itself and deepening the silence of its interior. So while we often describe the Boötes Void as nothingness, that word belies the reality. Its darkness is not the darkness of absence, but the darkness of concealment. Inside are the threads of dark matter, the wisps of intergalactic gas, the faint glow of hidden dwarfs, and the few lonely galaxies standing as islands in an ocean of emptiness. Its interior is not completely silent. It is whispering, faintly, in ways only the most sensitive instruments can detect. To study the Boötes Void is to peel back the layers of this subtle darkness and to realize that even emptiness has structure, content, and stories to tell. One of the most striking features of the Boötes Void is not just its emptiness, but the way the few galaxies it does contain are arranged. Astronomers who have studied its structure notice a clear trend. Most of its galaxies are not scattered randomly within the void, but instead tend to cluster around its periphery, lining its edges like faint lanterns outlining the walls of a colossal, invisible bubble. This pattern is not unique to the Boötes Void. It is a fundamental characteristic of cosmic voids in general. Yet, in a void so enormous, the effect is magnified, giving the impression that the universe has built a hollow sphere with galaxies and filaments wrapped around it, enclosing a cavern of near-total darkness at its center. This phenomenon, often called the bubble wall effect, is one of the clearest indicators of how matter in the universe organizes itself into the cosmic web. The explanation for this edge clustering lies in the physics of matter distribution. In the early universe, when tiny density fluctuations seeded the large-scale structure, gravity began pulling matter into denser regions. Over billions of years, these overdense regions grew into filaments and superclusters, while underdense regions, like the Boötes Void, lost matter to their surroundings. The gravitational migration of galaxies and dark matter away from void centers toward filaments naturally leads to a concentration of material at the void's boundary. This is why galaxies appear to outline voids instead of populating their interiors. The Boötes Void exemplifies this perfectly. Its few galaxies mostly inhabit the rim, forming part of the greater network of walls and filaments that define the architecture of the cosmic web. This clustering along the edges is not subtle. It creates some of the largest coherent structures ever observed. When astronomers map galaxies in 3 dimensions, they often see vast walls of galaxies that trace the boundaries of voids. Famous examples include the Sloan Great Wall, which spans over 1 billion light-years, and the CFA2 Great Wall, one of the first such structures ever discovered. These walls are not isolated. They are part of a continuous network that defines the shape of cosmic voids. The Boötes Void, being one of the largest known, is likely bordered by such walls, its spherical emptiness framed by immense galactic sheets. In a sense, the Boötes Void is less of a solitary hole and more of a chamber within the grand foam-like structure of the universe, its boundary glowing faintly with the light of galaxies pressed outward by billions of years of gravitational flow. To visualize this, imagine standing at the center of the Boötes Void and looking outward. At first glance, the sky around you would appear hauntingly empty, with almost no galaxies in sight. But as your gaze reached farther, the darkness would begin to be punctuated by faint smudges of light. These would not be evenly spread, but instead would form a shell, a dim and distant outline of galaxies arrayed along the void's edges. It would feel as though you were standing inside a hollow sphere, its walls glowing faintly with scattered galaxies, while the interior remained silent. That visual impression mirrors the actual structure astronomers detect when mapping the region. A cosmic bubble defined not by what is inside, but by what lies at its boundary. The galaxies that cluster along void edges are often more massive and more active than those in the interior. This is because they reside in denser environments where interactions are more common. Along the filaments and walls, galaxies are closer together, leading to more gravitational encounters, mergers, and bursts of star formation. In contrast, galaxies that find themselves stranded deep inside the void evolve more slowly, starved of interaction and fuel. The edge galaxies thus represent the frontier between abundance and emptiness, the places where the richness of the cosmic web pushes up against the silence of the void. By studying their properties, astronomers can learn not only about galaxy evolution, but also about the processes that sculpt the cosmic web itself. Interestingly, the bubble wall phenomenon also connects directly to the Boötes Void's role as part of the cosmic web. Far from being an isolated patch of nothingness, the void is woven into the universe's grand design. Its boundaries are part of the same filamentary structures that connect galaxies across billions of light years. In this sense, the Boötes Void is not a standalone object, but a feature of a much larger network. Its edge galaxies are like the beads on a thread, marking the points where matter accumulates along invisible filaments of dark matter. By mapping these galaxies, astronomers can trace the unseen scaffolding of the universe, using the void's boundary as a cosmic marker for where matter has gathered and where it has retreated. The presence of galaxies on the edge of voids also has implications for cosmological models. Simulations of the universe's evolution show that galaxies naturally migrate toward the boundaries of voids, leaving the interiors emptier over time. The Boötes Void, with its stark contrast between the barren center and the galaxy-rich rim, is a vivid confirmation of these predictions. It demonstrates how well our models capture the interplay of gravity, dark matter, and cosmic expansion. Yet, it also raises questions. Why is the Boötes Void so much larger and emptier than average? Are the processes at work here the same as in smaller voids, just scaled up? Or is there something unique about its formation that exaggerated its size and accentuated the clustering of galaxies along its edge? The bubble walls also serve as cosmic signposts for astronomers searching for the universe's largest structures. By mapping where galaxies cluster, scientists can infer the shapes and sizes of the voids they enclose. The Boötes Void's edge galaxies have helped reveal its spherical nature, distinguishing it from smaller, irregular voids. This makes it a particularly striking example of how voids and walls together form the fabric of the cosmic web, a kind of three-dimensional foam where the galaxies live on the thin films and the bubbles themselves are regions of silence. One of the most fascinating questions about the Boötes Void, and cosmic voids in general, is how they become so thoroughly empty over time. While density fluctuations in the early universe seeded the underdense regions that grew into voids, there is another dynamic process at play: the gradual migration of galaxies. Astronomers and cosmologists have long theorized that galaxies inside voids do not simply remain where they are forever. Instead, over billions of years, they slowly drift outward, drawn by the gravitational pull of denser filaments and clusters that surround the void. This slow but relentless movement of galaxies away from the centers of voids helps explain why regions like the Boötes Void appear so barren today. The underlying mechanism is gravity's universal tendency to pull matter toward areas of higher density. Imagine the universe as a vast landscape of hills and valleys where galaxies are like raindrops rolling downhill. The valleys represent dense regions rich with dark matter and galaxies, clusters and filaments, while the hills represent underdense regions, the voids. Over time, galaxies naturally migrate downhill, away from the voids and into the gravitational wells of the filaments. The effect is not fast on human timescales. It takes billions of years, but given the immense age of the universe, it is more than enough to gradually empty voids of their initial populations. The Boötes Void, therefore, may once have contained more galaxies than we see today, but over the course of cosmic history, many would have drifted outward toward its edge, leaving behind a vast hollow core. This process, often referred to as void evacuation, is well supported by cosmological simulations. When scientists model the growth of the universe from its early density fluctuations, they observe galaxies slowly migrating away from void centers as matter flows into filaments. These simulations reproduce the foam-like structure of the cosmic web, where voids are outlined by bubble walls of galaxies that have been drawn to the edges. The Boötes Void is an especially dramatic example of this process, its immense size making the migration effect particularly striking. Its sparse interior and galaxy-rich boundary are exactly what we would expect from billions of years of gravitational evacuation. What makes the idea of galaxy migration so compelling is how it transforms our understanding of voids as living, evolving structures. They are not static holes carved into the universe, but dynamic regions that change over time. In their youth, voids may contain a modest population of galaxies. As the universe evolves, those galaxies feel the gravitational tug of surrounding filaments, drifting outward in slow motion. Eventually, the voids become increasingly empty, their cores silent while their rims become denser with galaxies gathering along the edges. This paints a picture of voids as cosmic lungs, exhaling galaxies outward and leaving behind nothing but faint wisps of gas and dark matter. The galaxies that remain inside voids, however, are not completely exempt from this process. They are often the stragglers, those gravitationally bound to small dark matter halos that keep them from escaping. These galaxies can remain marooned in solitude for billions of years, evolving differently from their cousins in denser regions. They may form stars more slowly, retain unusual shapes, or even preserve primordial characteristics from earlier epochs of the universe. Studying them provides a glimpse into what galaxies might look like if left almost entirely alone, untouched by the gravitational interactions and mergers that dominate busier environments. Another fascinating consequence of galaxy migration is its contribution to the stark contrast between voids and filaments. As galaxies move outward, the voids grow larger and emptier, while the filaments become richer and more densely packed. This self-reinforcing cycle exaggerates the difference between abundance and scarcity across the cosmic web. In the case of the Boötes Void, the effect is taken to an extreme. Its interior, spanning 330 million light-years, is nearly barren, while its edge galaxies outline the structure like the skin of a bubble. This makes the void not just an anomaly of emptiness, but also a vivid demonstration of the dynamic processes that shape the universe's largest patterns. There is also the influence of dark energy to consider. As the universe's expansion accelerates, galaxies inside voids may be pushed outward even faster, their migration hastened by the stretching of space itself. In this scenario, voids like the Boötes Void are not only emptied by gravity's pull toward filaments, but also by the expansive push of dark energy that amplifies the process. This dual effect ensures that voids will continue to grow emptier as the universe ages, leaving behind vast stretches of silence broken only by the faintest of lights. The question of whether life could exist inside the Boötes Void is one of those profound thought experiments that sits at the intersection of science and philosophy. On the surface, the void seems like the least likely place in the universe to host life. It is vast, barren, and nearly devoid of galaxies, the very cradles of stars, planets, and biological possibilities. Yet, it is important to remember that emptiness does not mean impossibility. The handful of galaxies that do exist inside the Boötes Void, though lonely and isolated, are still galaxies. They still contain stars, planets, and the basic ingredients for life. In fact, their isolation may even create conditions so unique that if life were to arise there, it would evolve in solitude unlike anywhere else in the cosmos. To understand the potential for life in the Boötes Void, we must first consider the role of galaxies. Galaxies are the engines of cosmic creation, factories of stars, forges of heavy elements, and hosts to planetary systems. Even a single galaxy, no matter how isolated, could contain hundreds of billions of stars. Many of those stars would have planetary systems, and some of those planets might fall within the so-called habitable zone, where liquid water could exist. In principle, then, life could evolve inside the void, just as it does in denser regions of the universe. The basic physical processes that create stars, planets, and organic chemistry do not stop simply because a galaxy is surrounded by emptiness. However, what makes the Boötes Void fascinating is the extreme isolation of its galaxies. In denser regions of the universe, galaxies often interact, merge, and exchange material. These collisions can trigger bursts of star formation, enrich the interstellar medium with heavy elements, and stimulate the dynamism of galactic life cycles. Inside a void, such interactions are exceedingly rare. Galaxies evolve largely in solitude, without the frequent mergers that shape their counterparts in crowded environments. This has consequences for star formation rates, chemical enrichment, and galactic morphology. Void galaxies tend to be smaller, dimmer, and slower evolving. From a biological perspective, this could mean that planetary systems inside them are more stable, less frequently disturbed by galactic upheavals. Such stability could, in theory, provide a long, uninterrupted time span for life to emerge and evolve. But isolation also comes with challenges. Life, at least as we know it, depends not only on stars and planets, but also on the presence of heavy elements like carbon, oxygen, and nitrogen. These elements are forged in the hearts of stars and spread through galaxies by supernovae. In denser regions, where galaxies interact more often, the enrichment process happens faster. In void galaxies, star formation and supernova activity may be slower, meaning the chemical enrichment necessary for life could take longer. This raises the possibility that while life could exist in the Boötes Void, it may be less common, or it may arise later in cosmic history compared to galaxies in more crowded environments. Another factor to consider is the view from within the void. If intelligent life were to evolve inside one of these isolated galaxies, its perception of the universe would be dramatically different from ours. From Earth, when we look into the night sky, we see a tapestry of stars, and through telescopes we observe countless galaxies in every direction. For a civilization in the heart of the Boötes Void, the sky would be hauntingly empty. Beyond their home galaxy, there would be few nearby galaxies visible to the naked eye. Even with powerful telescopes, the surrounding universe would appear much less populated. Such a civilization might grow up believing their galaxy was the only one in existence, or that the cosmos was far more barren than it truly is. Their cosmology, philosophy, and even sense of significance would be shaped by this solitude. From a scientific standpoint, void environments could also create unique evolutionary pressures on life. If galaxies inside voids form fewer massive stars, there may be less radiation and fewer catastrophic supernova explosions threatening planetary systems. This could increase the chances of long-term stability for habitable planets. On the other hand, fewer massive stars also means less production of heavy elements and potentially fewer rocky planets overall. It is a delicate balance. Isolation may grant stability, but it may also starve galaxies of the raw materials needed to support rich ecosystems. There is also a more speculative angle. If intelligent civilizations do exist in void galaxies, they would be among the most isolated beings in the universe. Intergalactic travel, already daunting, would be exponentially harder in such regions. Neighboring galaxies might be tens or hundreds of millions of light years away, far beyond reach with any conceivable technology. A civilization in the Boötes Void would be alone in a literal sense, with no realistic chance of contact with others. Their entire existence would unfold in silence, their messages cast into an ocean of emptiness unlikely to ever be heard. From our perspective, this could make void civilizations virtually undetectable, hidden not by distance alone but by the profound scarcity of galaxies in their region. In this way, the Boötes Void becomes not just a question of astrophysics but of cosmic solitude. It forces us to ask, what does it mean for life to exist in isolation so extreme that the universe itself appears empty? Would such life be more fragile or more enduring? Would intelligence blossom differently when it perceives itself as utterly alone? These are questions we may never be able to answer, but they highlight the profound philosophical dimensions of the void. The Boötes Void, like other cosmic voids, can be thought of as a vast and silent desert in space, a place where the conditions differ profoundly from the bustling environments of galaxy clusters or superclusters. If the filaments of the cosmic web are crowded cities of the universe, full of galaxies colliding, merging, and triggering bursts of star formation, then voids are the empty wilderness, vast stretches of stillness where very little happens, and where galaxies, stars, and radiation are scarce. This cold desert is not cold in the everyday human sense. It is cold on a cosmic scale, reflecting both the lack of activity and the thinness of the matter that resides within. One of the defining environmental features of a void is its extremely low galaxy density. In a typical region of the universe, galaxies cluster together into groups and superclusters, often separated by only a few million light-years. In voids, however, galaxies are separated by tens or even hundreds of millions of light-years. Inside the Boötes Void, where only about 60 galaxies are known to exist across 330 million light-years. This separation is staggering. For a galaxy stranded near the center of the void, its nearest neighbor could be so distant that light would take tens of millions of years to travel between them. This isolation means fewer galactic interactions, fewer mergers, fewer bursts of star formation, and less exchange of material. The result is an environment that is quiet and slow, a cosmic desert where evolution takes place in solitude. Another consequence of this emptiness is the relative lack of stars. Galaxies themselves are rare, and those that do exist tend to be smaller and less active than their cousins in dense regions. Fewer massive galaxies means fewer massive stars, which in turn means less radiation overall. In galaxy clusters, the skies are filled with high-energy radiation from quasars, supernovae, and hot intergalactic gas. In voids, those sources are largely absent. The intergalactic medium inside voids is cooler and thinner, lacking the energetic processes that heat gas in crowded environments. This makes voids some of the coldest and quietest regions of the cosmos, true deserts, where the radiation background is faint and diffuse. The cold of the cosmic desert is not just metaphorical, it is measurable. The temperature of intergalactic gas in voids is significantly lower than in filaments or clusters. While dense regions can heat gas to millions of degrees through gravitational compression and supernova activity, void gas remains close to the temperature of the cosmic microwave background, just a few degrees above absolute zero. This makes voids ideal laboratories for studying pristine conditions of the early universe, since the gas there has been relatively undisturbed by the violent processes of galaxy formation and clustering. The Boötes Void, with its sheer size and lack of activity, is likely home to vast stretches of such cold, untouched gas, a fossil record of cosmic history preserved in emptiness. The radiation environment in voids also affects the galaxies that inhabit them. With fewer external sources of radiation, galaxies inside voids may evolve differently, shielded from the energetic influences that shape galaxies and clusters. They may form stars more slowly, with weaker bursts of star formation. They may also retain more neutral hydrogen gas, which in denser environments is often stripped away by interactions. These differences make void galaxies unique test cases for how environment shapes galactic evolution. In the cold desert of the Boötes Void, galaxies are like cacti in a barren landscape, adapted to solitude, surviving without the bustling exchanges that fuel growth elsewhere. Another dimension of the cosmic desert metaphor is the silence of voids. In dense regions, galaxies interact gravitationally, pulling at each other, colliding, merging, and sparking new cycles of creation. The cosmic web hums with activity. In voids, by contrast, such interactions are vanishingly rare. A galaxy drifting through the Boötes Void might never collide with another in the lifetime of the universe. It lives and dies in isolation, shaped only by its own internal processes and the faint gravitational whispers of its distant neighbors. This silence is part of what makes voids so haunting. They are not only empty, they are still. Yet, this stillness is not without importance. The cold desert of voids gives cosmologists an uncluttered stage to test theories of dark matter and dark energy. In dense regions, the signals of these invisible forces are muddied by the complexities of galactic interactions. In voids, the simplicity of emptiness makes their effects clearer. The accelerated expansion driven by dark energy, for example, shows up most strongly in voids, where gravity cannot counterbalance it. Likewise, the distribution of dark matter in underdense regions provides key insights into how structure forms across the universe. The Boötes Void, as one of the largest such deserts, is therefore more than an empty space. It is a natural laboratory, stripped bare of distractions, where the universe reveals its underlying laws. For all their emptiness, voids like the Boötes Void are far from irrelevant in the grand tapestry of cosmology. In fact, many astronomers consider them some of the most valuable regions in the universe for testing fundamental theories about how reality itself works. Their very emptiness is what makes them useful. Stripped of the clutter of crowded galaxy clusters and the chaotic fireworks of mergers and supernovae, voids provide pristine laboratories where the subtle influences of dark matter, dark energy, and gravity can be studied with far fewer distractions. In this sense, they are not merely the deserts of the cosmos. They are the testing grounds where some of the most profound mysteries of science may finally be solved. One of the primary reasons astronomers study voids is their relationship with dark matter. Though we cannot see dark matter directly, its fingerprints are everywhere in the universe. It provides the gravitational scaffolding around which galaxies form, and it shapes the large-scale structure of the cosmic web. But in dense regions like clusters, the behavior of dark matter is masked by the overwhelming presence of baryonic matter, stars, gas, and dust that dominate observations. In voids, however, visible matter is scarce. This makes voids particularly sensitive to dark matter's gravitational influence. By mapping the shapes and boundaries of voids, astronomers can infer how dark matter is distributed and test whether its properties align with predictions from cosmological models. The Boötes Void, being one of the largest, is a key example. Its scale and emptiness amplify the subtle signatures of dark matter, making it an extraordinary natural laboratory for exploring the invisible. Voids are also crucial in the study of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are underdense, gravity has less influence in them than in clusters or filaments. This means that dark energy dominates voids more strongly, stretching them faster than denser regions. By measuring how voids expand and evolve over cosmic time, astronomers can test models of dark energy. If dark energy is a simple cosmological constant, voids should expand in a predictable way. But if it evolves or behaves differently than expected, voids may reveal those deviations first. The Boötes Void, in particular, with its sheer scale, magnifies these effects. Observing its growth and comparing it with simulations provides one of the most direct ways of probing whether our understanding of dark energy is correct, or whether new physics is required. Another reason voids are studied is that they provide insights into the geometry and structure of the universe itself. On large scales, the cosmos is expected to be isotropic and homogeneous, uniform in all directions. Yet, voids like Boötes challenge us to refine that picture. Their existence, size, and distribution help cosmologists test whether the large-scale structure we observe truly matches the predictions of the standard cosmological model. If voids are larger, emptier, or more irregular than expected, this could hint at missing pieces in our theories of gravity or cosmic evolution. In this sense, voids act like stress tests. By pushing our models to their limits, they reveal whether the scaffolding of modern cosmology holds up under scrutiny. One particularly promising technique in this field is the integrated Sachs-Wolf effect, a phenomenon where light from the cosmic microwave background, CMB, the afterglow of the Big Bang, is subtly altered as it passes through large-scale structures. In clusters, the gravitational pull deepens the energy of photons, while in voids, the opposite occurs. Photons lose energy as they climb out of shallower gravitational wells. By studying how the CMB is distorted when passing through voids, astronomers can measure the imprint of dark energy on cosmic scales. The Boötes Void, given its vast size, has the potential to produce one of the most noticeable void-related signatures of this effect, making it an especially valuable target for study. Voids are also laboratories for understanding galaxy evolution under isolation. The galaxies inside them, though few, provide natural experiments in how environment shapes development. In crowded regions, galaxies constantly interact, colliding, merging, and triggering starbursts. In voids, these processes are rare. Galaxies there evolve more slowly, often retaining characteristics that have long since vanished in denser areas. They are smaller, more gas-rich, and less chemically evolved. By comparing void galaxies with those in clusters, astronomers can disentangle how much of a galaxy's evolution is intrinsic and how much is dictated by environment. In the case of the Boötes Void, its few galaxies are cosmic loners, growing old in silence. perfect case studies for environmental effects on galactic life cycles. Even the shapes of voids themselves hold scientific value. Voids are not always perfect spheres. They can be stretched or distorted depending on how matter flows around them. These distortions, when carefully measured, reveal the fingerprints of cosmic expansion and the growth of structure over time. They allow scientists to test alternative theories of gravity, some of which suggest that the laws of gravity may behave differently on cosmic scales than they do within our solar system. Voids, being dominated by expansion rather than collapse, are sensitive to these deviations. The Boötes Void, enormous and unusually spherical, provides a striking case study in whether these models hold true. The Boötes Void is often described not only as one of the largest voids in the universe, but also as one of its greatest anomalies, a cosmic feature so extreme that it pushes against the boundaries of our models of large-scale structure. While astronomers understand that voids are a natural byproduct of the universe's evolution, the Boötes Void's staggering size and near-total emptiness make it stand apart from all others. At 330 million light-years across and containing only about 60 galaxies where thousands should exist, it challenges us to ask whether our current cosmological theories fully capture the processes that give rise to such immense hollows. In many ways, the Boötes Void is not simply a void. It is an enigma that forces us to confront the possibility that our understanding of the cosmic web is still incomplete. Voids themselves are not unusual. They are expected outcomes of the Big Bang's initial conditions. Regions that began slightly underdense grew emptier as gravity pulled matter toward denser filaments. In simulations of the universe, voids appear naturally, scattered like bubbles in a cosmic foam. But what makes the Boötes Void so anomalous is its sheer scale. Most voids range from 20 million to 100 million light-years across. Even the larger supervoids, such as the Eridanus supervoid, linked with the CMB cold spot, rarely exceed 200 million light-years. The Boötes Void, at 330 million, is an outlier of staggering proportions, more than 3 times the size of a typical large void. This raises a serious question. Is it simply a statistical fluke, the result of chance fluctuations magnified over cosmic time, or does it represent something deeper? Perhaps new physics we have yet to uncover? Some cosmologists argue that the Boötes Void may be one of those rare statistical extremes predicted, but not commonly observed in the standard lambda cold dark matter model. According to this model, the distribution of void sizes should follow a pattern, with smaller voids being far more common than larger ones. The Boötes Void sits at the extreme tail of that distribution, so rare that we would not expect to find many like it in the observable universe. Yet the fact that we did find one, close enough to study, makes it a kind of cosmic jackpot, a discovery that feels almost too extreme for comfort. If it is an outlier, then it is an extraordinary one, pushing our theories to account for the possibility of such vast underdensities. But others suggest that the Boötes Void might reveal limitations in our models. Perhaps our understanding of dark matter, dark energy, or cosmic inflation is incomplete, and the existence of such an extreme void points to gaps in the framework. For example, some theorists have proposed that non-standard forms of dark energy, those that vary over time rather than remaining constant, could exaggerate the emptiness of voids, causing them to grow larger than expected. Others speculate that voids like Boötes could be linked to subtle variations in the inflationary field that seeded the universe's density fluctuations. If so, the Boötes Void is not merely a curiosity, but a fossil from the earliest moments of creation, carrying within its emptiness a hidden record of the forces that shaped the cosmos. The anomaly of the Boötes Void also forces us to rethink the balance of cosmic structure. The cosmic web is a universe of contrasts, filaments and voids, density and emptiness, light and silence. But the Boötes Void skews this balance so heavily toward emptiness that it feels almost unnatural. It is not just underdense, it is profoundly, almost unnervingly barren. Even accounting for faint dwarf galaxies that may yet be discovered within it, the void remains far emptier than theory predicts. This mismatch between expectation and observation is what cements its status as a cosmic anomaly. It suggests that there may be unknown processes, whether physical, gravitational, or quantum, that have accentuated its size. The Boötes Void also unsettles our intuitive sense of cosmic uniformity. One of the guiding principles of cosmology is the cosmological principle. On sufficiently large scales, the universe should be homogeneous and isotropic, uniform in all directions. The Boötes Void, however, seems to strain that principle. While one anomaly does not disprove the rule, its existence raises the question, how uniform is the universe, really? If more voids of comparable size were to be found, it might suggest that the universe is clumpier and less homogeneous than our models predict. On the other hand, if the Boötes Void remains unique, then its singularity only deepens the mystery of why it exists at all. Another reason the Boötes Void is regarded as a cosmic anomaly is the psychological effect of its scale. Even though astronomers are trained to deal with enormous numbers, the Boötes Void is so vast and so empty that it feels almost alien, like a scar in the fabric of reality. In a universe teeming with trillions of galaxies, to encounter a region this barren is unsettling. It forces us to confront the possibility that the universe contains features so extreme they defy our expectations. For this reason, the Boötes Void has often been referred to as the Great Nothing, not just for its physical emptiness, but for the way it embodies the unsettling possibility of limits to our understanding. Some scientists have even suggested that the Boötes Void might be more than just a void. It could be part of a larger, hidden structure. Perhaps its emptiness is exaggerated by connections to neighboring voids, forming a kind of supervoid complex larger than we realize. If true, then the Boötes Void may be only a piece of a grander architecture, part of an even larger anomaly waiting to be fully mapped. Others propose that it could harbor faint or exotic forms of matter invisible to our instruments, hinting at new physics or undiscovered structures. While these ideas remain speculative, they underscore how the Boötes Void has become a focal point for questioning the adequacy of our current cosmological models. Philosophically, the Boötes Void challenges our perception of the universe as a place of abundance. We are accustomed to thinking of the cosmos as overflowing with galaxies, stars, and planets. The void reminds us that emptiness is just as much a part of the story, and sometimes emptiness can be stranger than abundance. Its status as an anomaly forces us to expand our imagination, to accept that the universe may not always conform neatly to our expectations. It is a humbling reminder that even with all our progress in mapping the cosmos, there remain features so extreme that they resist easy explanation. Ultimately, the Boötes Void stands as both a confirmation and a challenge. It confirms that voids are real, expected, and fundamental to the cosmic web, but it challenges us by showing that voids can reach scales so vast and so empty that they strain the models we rely on. It is both a predictable outcome and an extraordinary outlier, both natural and anomalous. And in that paradox lies its power. The Boötes Void is not simply a hole in the universe, it is a hole in our understanding, one that demands to be filled not with matter, but with knowledge. The Boötes Void's staggering size and near-total emptiness have naturally given rise to speculation far beyond the standard explanations of density fluctuations and cosmic evolution. While mainstream cosmology attributes its existence to the natural growth of structure after the Big Bang, some scientists and thinkers have entertained alternative hypotheses to explain why this particular void is so extreme. After all, even in a universe where voids are expected, one as vast and barren as Boötes feels like an outlier, anomalous enough to tempt us toward more exotic possibilities. These alternative ideas range from cautious scientific speculation to imaginative hypotheses that test the very limits of physics. One line of speculation suggests that the Boötes Void might not be a true void at all, but could contain hidden structures we simply cannot detect yet. For example, the galaxies inside it may be dominated by faint dwarf galaxies or low-surface brightness galaxies that evade current instruments. Such galaxies could be numerous yet invisible, forming a ghostly population that fills the void more than we realize. If future telescopes like the James Webb or next-generation surveys such as the Vera Rubin Observatory reveal vast numbers of these hidden galaxies, then the Boötes Void's emptiness might be less severe than it appears. However, even this explanation has limits, because even if dwarfs are found, they would not be enough to account for the thousands of galaxies expected in a region this large. The anomaly would remain, though perhaps softened. Another possibility is that the Boötes Void is influenced by dark matter in unexpected ways. In the standard model, dark matter provides the gravitational framework for galaxies to form. If the void's dark matter density is unusually low, then galaxies would simply fail to take root. But some scientists have speculated that perhaps dark matter behaves differently in underdense regions than it does in denser ones. If its properties vary in ways not yet understood, it could amplify the emptiness of voids like Boötes. Some even suggest that self-interacting dark matter, or exotic dark matter particles, might alter how structure forms on large scales. In this view, the Boötes Void may be a signpost pointing to new physics in the dark sector, a clue that the invisible majority of the universe is more complex than we currently imagine. Others take the idea further, proposing that the Boötes Void may hint at modifications to gravity itself. The standard model of cosmology relies on Einstein's theory of general relativity, which describes how gravity operates across all scales. But some alternative theories, such as modified Newtonian dynamics, MOND, or other extensions of relativity, suggest that gravity might behave differently in low-density regions. If so, voids like Boötes could be exaggerated by these non-standard gravitational effects. The galaxies we see clustering along its edge could represent a natural boundary formed not just by matter distribution, but by gravity acting in unfamiliar ways. This hypothesis remains highly speculative, but voids are among the few environments where such alternative theories can be tested without interference from dense galactic environments. Even more exotic hypotheses have been floated, ideas that stretch the imagination but capture the sense of mystery the Boötes Void inspires. Some have suggested that it could have the imprint of primordial physics from the earliest moments of the universe, such as topological defects left over from cosmic inflation. Inflation was the rapid expansion that smoothed out the universe in its first fraction of a second. But if that process left behind irregularities, cosmic strings, textures, or domain walls, they might manifest as large-scale anomalies like extreme voids. Though there is no direct evidence tying the Boötes Void to such exotic relics, the idea highlights how unusual structures can force us to look back to the very origin of the universe for answers. There are even more speculative and, at times, fringe interpretations. Some have wondered whether the Boötes Void could be the result of vast astrophysical processes we do not yet understand, such as ancient waves of star formation and collapse that evacuated its contents, or regions where galaxy formation simply failed due to unusual conditions in the early universe. Others, leaning more toward philosophical speculation, have imagined it as a kind of cosmic scar, the residue of events so ancient or so exotic that their causes are lost to us. While these ideas are not mainstream science, they reflect the unsettling nature of the void. Its scale is so extreme that it almost begs for explanations beyond the ordinary. Among the most imaginative hypotheses is the idea that the Boötes Void could be linked to cosmic multiverse theories. In some models of the multiverse, our universe is just one bubble among many, each with different physical laws. If regions of our universe brushed against others during inflation, they might leave behind imprints, vast anomalies like the Boötes Void. Though highly speculative and lacking empirical support, this possibility captures the sense of awe the void inspires. If true, it would make the Boötes Void not just a hole in the universe, but a boundary where universes themselves have interacted. Even outside scientific circles, the Boötes Void has fueled more speculative imaginations, some calling it the Great Nothing, as though it were a cosmic error, others half-jokingly wondering if it is an artificial structure, a region deliberately emptied by forces unknown. While such ideas stray far from science, they underline the human response to anomalies. When faced with something so extreme, we naturally reach for extraordinary explanations. Still, the mainstream view remains grounded. The Boötes Void is most likely an unusually large but natural underdensity, born of quantum fluctuations during inflation and stretched by billions of years of cosmic evolution. Yet the persistence of alternative hypotheses underscores its uniqueness. Unlike ordinary voids, it has a scale that leaves room for doubt, for curiosity, and for wonder. Scientists are drawn to it not only because it fits into the cosmic web, but because it does not fit neatly enough. It leaves us with lingering questions. In this way, The Boötes Void functions as both a scientific puzzle and a philosophical mirror. Its emptiness forces us to confront the possibility that the universe still hides layers of physics we have yet to uncover. Whether the answer lies in hidden galaxies, dark matter's mysteries, modified gravity, or something stranger still, the Boötes Void remains an open question, a space where speculation thrives, and where the silence of the cosmos speaks volumes about how much we have yet to learn. For all its vastness and silence, the Boötes Void is not a closed case. It is a mystery still unfolding, and the next generation of telescopes and surveys may finally pierce its darkness to reveal what truly lies inside. While current observations confirm only about 60 galaxies within its staggering 330 million light-year span, that number is almost certainly incomplete. Many of the galaxies inside the void may simply be too faint or diffuse to be seen with existing instruments. Modern tools like the James Webb Space Telescope, JWST, along with upcoming projects such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, and the European Space Agency's Euclid mission, hold the potential to uncover faint galaxies, hidden structures, and even entirely new properties of voids that we cannot yet imagine. The James Webb Space Telescope is already transforming our understanding of faint, distant galaxies by peering deeper into the cosmos than any observatory before it. With its infrared vision, JWST is perfectly suited to detect low surface brightness galaxies or faint dwarf galaxies that may populate the Boötes Void. Such galaxies are notoriously difficult to see in optical light, but JWST can pick up their glow across billions of light years. If hundreds or even thousands of these faint galaxies are revealed within the void, the picture of its emptiness may shift dramatically. It would still be underdense, but perhaps not as barren as it appears today. On the other hand, if JWST finds very few hidden galaxies even at its extreme sensitivity, the void's reputation as one of the universe's most profound anomalies would only be strengthened. Future ground-based surveys will also be critical. The Vera C. Rubin Observatory, with its 10-year legacy survey of space and time, is designed to create the most detailed map of the sky ever made. It will track billions of galaxies, including faint and diffuse ones that may have been overlooked in past surveys. Rubin's wide-field view will allow astronomers to chart the structure of the Boötes Void in unprecedented detail, tracing its boundaries, mapping its sparse interior, and possibly uncovering hidden dwarf galaxies along its edge. Such data will help refine our models of void formation and provide new insights into how galaxies evolve in isolation. Meanwhile, the Euclid mission, launched in 2023, is specifically tasked with studying dark energy and dark matter by mapping the large-scale structure of the universe. Voids, like Boötes, are central to that mission. By precisely measuring the shapes and distributions of voids, Euclid will help determine whether dark energy behaves as predicted by the standard cosmological model or whether it evolves over time. The Boötes Void, with its size and emptiness, is an ideal candidate for such study. Its very existence provides a kind of stress test for cosmological theories, and Euclid's data may reveal whether it conforms to predictions or points toward new physics. But what might we actually discover inside the void? One possibility is the detection of faint dwarf galaxies scattered through its vast interior. These galaxies, with only a few million stars each, are hard to detect but could exist in greater numbers than we currently know. If found, they would reshape our picture of the void, showing that while it is still underdense, it contains a hidden population of galaxies that has so far eluded our view. Such a discovery would also teach us about the limits of galaxy formation. How small can galaxies be? And how do they evolve when marooned in solitude for billions of years? Another possibility is uncovering diffuse gas filaments threading through the void. Even in emptiness, the intergalactic medium is never truly absent. Detecting faint hydrogen gas in the Boötes Void would help scientists map the cosmic web's hidden threads and better understand how matter is distributed even in underdense regions. With instruments sensitive to subtle absorption features in quasar light, astronomers can trace this gas and determine whether voids are completely barren or if they still contain tenuous wisps of cosmic material. There is also the tantalizing possibility that we may discover new properties of physics within the void. For example, if dark energy behaves differently in low-density regions, Its effects could be revealed most strongly inside voids like Boötes. Careful mapping of its expansion and the behavior of its few galaxies may reveal anomalies that cannot be explained by the standard cosmological model. This would push us toward new theories of dark energy, gravity, or even the fundamental nature of space-time. Another avenue of discovery involves studying the isolated galaxies already known inside the void. With better instruments, astronomers can measure their star formation rates, chemical compositions, and evolutionary histories in detail. If they turn out to be significantly different from galaxies in denser environments, they may reveal how isolation changes the path of galactic evolution. Do they form stars more slowly? Do they preserve primordial characteristics erased in cluster galaxies? Each lonely galaxy inside the void is a unique experiment, and studying them could unlock secrets about how galaxies grow and survive without external influence. Even more speculative is the possibility of discovering entirely new structures we do not yet anticipate. The Boötes Void is so extreme that it may harbor phenomena invisible to our current understanding. Faint gravitational effects of dark matter clumps, diffuse star streams, or relic structures left over from cosmic inflation. As our instruments grow more sensitive, we may find that the void is not just empty space, but a subtle canvas painted with the faint traces of processes we cannot yet explain. In the coming decades, the Boötes Void will almost certainly become a focus of exploration as these new observatories come online. Each new discovery, whether hidden galaxies, faint gas, or unexpected physics, will deepen our understanding of not just this one void, but of the universe itself. And even if future surveys confirm that it is as empty as it appears, that confirmation will be just as significant. It would cement the Boötes Void's role as one of the most extreme natural structures in the cosmos, a vast silent chamber that embodies the universe's capacity for both abundance and absence. The mystery of the Boötes Void is far from over. In fact, it may only be beginning. For now, it remains the great nothing, but with the power of our modern telescopes, we are poised to find out whether its silence hides faint whispers of galaxies, gas, and physics, or whether it truly is one of the most profound voids in all of existence. The Boötes Void is more than a cosmic structure. It is a symbol. When we think about the universe, our imaginations instinctively leap to the luminous, stars blazing with nuclear fire, galaxies swirling in majestic spirals, nebula glowing like painted clouds. We imagine activity, motion, and abundance. Yet the Boötes Void turns this expectation on its head. Instead of being defined by what it contains, it is defined by what it lacks. It is a place where silence outweighs sound, absence outweighs presence, and darkness overshadows light. In its immensity and emptiness, the Boötes Void reminds us that one of the universe's greatest mysteries may not be what is there, but what is missing. This silent kingdom, stretching 330 million light-years across, dwarfs every human scale of measurement. To cross it at the speed of light would take longer than the time it took life to evolve from primitive ocean organisms into humans. Entire epochs of planetary history, mass extinctions, continental shifts, the rise and fall of species, would unfold, and still the traveler of light would not have reached the other side. And yet, for all that vastness, there are only about 60 galaxies scattered thinly within it. 60 islands of light adrift in an ocean of shadow, each one separated from the others by distances so great that the mutual existence is almost meaningless. This is the Boötes Void. Not chaos, not violence, but stillness. The silence inside the void is not an absence of laws or processes, it is the expression of them. Matter flowed toward denser filaments, galaxies migrated outward, and dark energy continued its relentless push, leaving the Boötes Void increasingly empty with every passing billion years. It is a kingdom sculpted not by destruction but by retreat. The galaxies within it are not victims of some cosmic catastrophe. They are survivors of solitude. They shine faintly, untouched by frequent collisions or mergers, living their quiet lives in isolation. And in their stillness, they bear witness to the slow, patient hand of cosmic evolution. Yet the Boötes Void's silence is not only physical, it is philosophical. For us, creatures who have spent millennia mapping the heavens, the discovery of such an immense emptiness is humbling. We are accustomed to a universe overflowing with galaxies, where every patch of sky is thick with light. To confront the Boötes Void is to confront the possibility that the universe is not primarily about fullness, but about emptiness. Galaxies are not the rule. They are the exception. The true substance of the universe is void, and matter is but the embroidery on its surface. This inversion of expectation is unsettling because it reminds us that our perspective, based on living in a relatively crowded corner of the cosmos, is not universal. In another place, in the heart of the Boötes Void, an intelligent being might gaze at the night sky and believe the universe was almost barren, devoid of other galaxies, devoid of other possibilities. And this raises a haunting question. What does it mean for life, for meaning, to exist in such solitude? A civilization inside one of the few galaxies in the Boötes Void would grow under a sky almost empty of neighbors. Perhaps their telescopes would reveal faint smudges on the cosmic horizon, but they might conclude that the universe is a lonely place, devoid of the richness we know exists elsewhere. To live in the void would be to live in existential solitude, a kingdom of silence where the idea of connection to the wider cosmos might never occur. And yet, perhaps in that solitude, such a civilization might also find resilience, evolving not in competition with others, but in harmony with their own world, under skies dark enough to let them see the faintest whispers of the cosmos beyond. The Boötes Void also forces us to reflect on the nature of discovery itself. When astronomers first mapped it in the 1980s, it seemed almost like a mistake, a hole in the data. But it was no error. It was reality asserting itself in a way we had not imagined. And this is perhaps the greatest lesson the Boötes Void offers, that the universe is not obligated to fit our expectations. It contains wonders and anomalies, not because they are convenient to our models, but because reality is larger, stranger, and deeper than we can conceive. The Boötes Void is a reminder that every map we draw, every model we build is provisional. There will always be anomalies, always be surprises, always be silences too deep to ignore. As we look to the future, the Boötes Void will remain one of the most compelling laboratories for astronomy. The James Webb Space Telescope, the Rubin Observatory, and missions like Euclid will peer deeper into its darkness, searching for faint dwarf galaxies, diffuse gas, and signatures of dark matter and dark energy. They may find more light than we expect, or they may confirm its emptiness even more starkly. Either outcome will deepen our understanding. If more galaxies are revealed, we will learn about the hidden populations that thrive in solitude. If not, then the void will stand as a profound anomaly, a puzzle demanding answers from the most fundamental levels of physics. In either case, the Boötes Void ensures that science will always have mysteries left to explore. But beyond the science, the Boötes Void resonates because it touches something deeply human, our relationship to silence. On Earth, we are surrounded by activity, cities filled with noise, skies filled with stars. Yet, when we step into deserts, caves, or deep oceans, silence confronts us. It is alien, overwhelming, and profound. The Boötes Void is the universe's version of this silence. It is the desert of the cosmos, a place so empty it feels unnatural, yet so vast it redefines what natural means. To contemplate it is to confront the scale of absence, to realize that nothingness can be as awe-inspiring as any nebula or supercluster. Ultimately, the Boötes Void is not chaos, but order. It is not a mistake, but an outcome. It is not frightening because of what it contains, but because of what it does not. And in that absence lies its majesty. It is a silent kingdom, a reminder that the universe is not merely a tapestry of light, but also a canvas of shadow. Its greatness lies not in abundance, but in the emptiness that makes abundance meaningful. When we gaze into the Boötes Void, we are reminded of the paradox at the heart of existence, that absence can define presence, that silence can amplify sound, and that what is missing can be as profound as what is found. Inside the Boötes Void lies not chaos, but silence, and in that silence the universe whispers its deepest truth, that the greatest mystery may not be what we see, but what we do not. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.